Okay, can I start?
I'll just give firstly an introduction,
Yeah.
introduce you as well. So, good afternoon,
Yeah.
everyone, and thanks for attending the CAR webinar today. I am Farhad Salimi, and I'm a postdoc at CAR and will host today's seminar. Today's presenter is Associate Professor Yuming Guo, who is an NHMRC Career Development Fellow at Monash University School of Public Health and Preventive Medicine. His research areas are environmental epidemiology, biostats, global environmental change, air pollution, climate change, and infectious disease modeling. Now, I would like to ask Yumi to start his seminar titled Random Forest Model to Estimate PM2.5 Exposure with Remote Sensing, Land Use Information, and Meteorological Data. You can start, Yumi. Thank you.
Thank you, Fahad. Can you hear me clearly?
I can, yes. That sounds
My
great.
voice loud?
That's
Okay. Thank you, and good afternoon, everyone. I'm very pleased to give a presentation for the random forest model to estimate PM2.5 exposure with remote sensing, land use information, and weather conditions. Um, okay. Yes, here is some background why we want to estimate air pollution. I think everyone wants to live in a very clean air because it is very healthy But sometimes it is not as you want. It is polluted with very serious air pollution. Here is the context of PM5 in the world. We can see in China, North India are high polluted by air pollution and some areas of South Africa. And for many years ago, there is evidence for the relationship between air pollution and health, particularly from 1955, 1952. Yes. Particularly from 1952, there is a very heavy smog in London. There is a very clear evidence with the increase air pollution. There were many deaths because of time. Many studies were conducted to look at the effect of air pollution on health, not only for short-term effect, but also for long-term effect. So why we estimate PM2.5? There are many reasons, but the most important two reasons are there are limited measurement data for PM2.5. For not only for space scale, for example, there are limited measurement monitors for only located in the urban sites and no monitor stations in rural areas. And also, the monitoring stations were established only after 2000 or 2005, 2010, and there is a limited time scale. So we need to measure the PM5 in both space scale and time scale. And there is an emerging topic to look at the air pollution effect on health outcomes. If we don't have enough PM2.5 data, we can't assess the health effect. So what variables can be used to estimate PM2.5? There are many studies have been tried to look at predicting PM2.5 at a global scale, at local scale, and some of them at province scale and national scale. The most important variable is satellite AOD data, because this is an index to reflecting the air pollution, particularly for PM5, PM10. And another important variable is land use information, because they are related to the concentrations of distribution of PM. This information includes greenness, road density, urban cover, and other variables. And another important variable is the weather conditions, because several studies have give a relationship between temperature and PM2.5, relative humidity and PM2.5, rainfall and PM2.5, and wind speed and PM2.5. Uh, this has been confirmed by many studies. Mm. And another important thing is the spatial temporal correlations and trends. For example, there is a spatial correlation uh, for the PM2.5 in the urban area, and there is a time correlation for the PM2.5 distribution. Besides these variables, there are some other variables that can be used to predict PM2.5. For example, the wildfire population density and other variables. Okay, and which models can be used to estimate PM2.5? At the beginning, some studies tried to use a very simple linear regression with some important interpretable variables. For example, they use simple linear regression uh, to link the monitoring station, monitor the PM2.5 and land use information and weather conditions to predict the ground level of PM2.5. But because the linear regression has some strictures and some limitations, and the generalized linear regression and generalized additive regression was started to be used to link the ground level PM5 and the predictable variables. Because the relationship between ground level PM5 and the predictive variables is not simple, it's a complex one. So a mixed effect model was developed to link their relationship to give some random effect for the time or for the day of the week, for the month, and using fixed effect for the uh, AOD and land use information, weather conditions. And another important model is Kriging. That is simple, just using the spatial correlation uh, effect for the PM5 and using universal Kriging or ordinary Kriging to do some prediction for PM5. And recently, a Bayesian spatial temporal model is also developed to link the ground level PM5 and the predictable variables to predict PM5. Uh, in the last 3 or 5 years, there are some studies uh, tried to use machine learning method and deep learning method to predict PM5 because these models can handle very complex relationships and you don't need to give some assumptions. So here I want to introduce why we use random forest model to predict PM2.5 because this is widely used in this area. I think there are more than 20 or 30 papers have been published to link PM2.5 and predictable variables to estimate ground level PM2.5 concentrations. So why we use this one? Uh, because random forest model is an ensemble classifier that consists of many decision trees and outputs the classes. That is the mode of the classes output by individual trees. This is um, different with decision trees. Decision trees is only one tree, but random forest trees is many decision trees combined together, not only one. This can overcome the limitations of decision trees. And the second one is the term, this this method is first proposed by Tin Cam Ho of Biolabs in 1995, and this is advanced by Breman's bagging idea and the random selection of features. This is very important using bagging idea. This is make this area very advanced. This is some other reasons why we use random forest model. From our experience and from some other studies, it is one of the most accurate learning method. Uh, for many datasets, it produces highly accurate classifier and high predictive ability. And the random forest model runs efficiently on large datasets, and it can handle thousands of input variables without variable deletion. And also, it gives estimate of which variables are important uh, based on the importance of a variable score. And it gives an internal unbiased estimate of a generalization error as the forest building progress. And it has an effective method for estimating missing data and maintains accuracy when a large proportion of the data are missing. But there are still some disadvantages of a random forest model. For example, it is a black box. We don't know what is the details of the relationship between the predictive variables and predicted variables. And the relationships are not easily to interpret. And this is a complex model. It is much harder and time consuming to construct than the decision trees. Even it is much harder than decision trees, but the predictive ability is higher than decision trees, and we don't need to cut the trees because decision trees it can overfit for many times. And another one is random forests has been observed to overfit for some data set. But even there are some overfit for some data set, but it is not always happened. Um, but decision trees can have overfit for many times. And the last one is if we use a random forest for the data, including categorical variables with different numbers of levels, it can bias the attribute with more levels. So if we use the random forest model for this type of data, the variable importance score is not reliable. We need to find another method to judge it. So which package can be used for a random forest model? So because I use R, so I introduce the random forest package for you if you want to use in the future. Hey, I want to introduce an example using random forest model to predict PM2.5 in China. We got PM2.5 data from about 1,500 stations. That is from 2014 to 2016 for daily concentrations. And we downloaded the MODIS AOD data from NASA. It including dark package and deep blue from Aqua atmosphere level 2 product collection at 10-kilometer resolution. That is covering China, the whole China. And to increase the spatial coverage of AOD data, we use approach from other study to fill the missing values in both products and combine them using a mixed model. And also we got meteorological data from 824 weather stations covering China. This data includes daily mean temperature, relative humidity, air pressure, and wind speed. Because this data only from 824 weather stations. So there are some areas don't have the weather station, and then we use a microcurrent from our package to interpolate the weather variables for the areas where didn't have weather data. And also we download some land use information and vegetation from NASA. And we also had other spatial predictors that include active fires from NASA fire information for resource management system. And also we get elevation data for the whole China. And this data was downloaded from CGIAR consortium for spatial information. Here is the model development. We developed 3 models to compare which model is best. The first model is the random forest model. The second model is the generalized additive model. And the third model is generalized additive model with the exposure response lag model. For the random forest model, for all these models, we include AOD, temperature, relative humidity, blood pressure, wind speed, NDVI, urban cover, and the day of the year, and log scale of elevation into the model to link these variables with the ground measurement of PM2.5. And after we develop this model, we can validate their performance and predict the ground level PM2.5. I want to highlight what is the exposure response lag model. The exposure response lag model is we consider the lag effects of temperature on PM2.5. For example, today's PM2.5 is not only related to today's temperature, but also affected by yesterday or the day before yesterday's temperature. So we give a function for the exposure response lag in the model. And we use a 10-fold cross-validation method to validate our predictions, to validate which model is better. And we also get the overall adjusted R-square and RMSE to compare which model perform better. So here's the results for the 3 models. The top one, the top row is the model performance from random forest model. We can say for the random forest.
The
Hello.
screen I'm watching on my. Hello.
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 Yes. Do you have any question?
No, sorry. I'm just. I just said. At least I got connected now. Sorry. Thank you.
Okay. Yes. For the top row, that is the results, the validation results from random forest model. We can say for the daily PM2.5, the R-square is 83%, and the RMRCE is 18. And the middle row is the results from the GAM model, generalized additive model. We can say for the daily model, the R-square is 55%, and the RMSE is 29. And the bottom row is the results from GAM with exposure lag response model. We can say the R-square 51% and the RMSE is 30. So, and this is the daily. The left column is the daily prediction, The middle column is the monthly prediction, and the left column is the annual prediction. We can see for all of them, the random forest model give a higher prediction than other two. Then we use the random forest model to predict PM2.5. So here is our prediction for the PM2.5 for the whole China at 10 kilometer resolution. We can see, in China, the Beijing, Tianjin, Hebei area is highly polluted, and in the high Shandong province, it's also high polluted. And we can divide the data into spring, summer, autumn, and winter. And we can see PM2.5 concentration was higher in winter than other seasons. And also we can see the long-term trend for the PM2.5 concentration. We can see during 2005 and 2008, there is an increase of PM2.5, but started to decrease from 2008 because the China government put a lot of effort to reduce air pollution. So what will we do for this from this work? So this work proposed a new method with high predictive ability to estimate air pollution and to understand the spatial temporal variation of PM2.5. And it provides the possibility to assess the health impact of PM2.5 by linking the estimated PM2.5 to the health data. We have some plan for the future work. The first thing is we want to apply this same model to Australia context. And also we want to find a method to interpolate the missing satellite AOD data, because there are many missing data because of the cloud coverage. And also we want to compare different models because we still don't know the other models' performance. For example, extreme gradient boosting model and the neural network model and the other deep learning model and machine learning model. Okay, thank you very much.
Thanks, Yuming. It was a very interesting presentation and seems to be a very technical and hard work to do as well. So to anyone who has a question, we will have now, I think we have time at least 15-minute Q&A. So if you look at your GoToMeeting panel, there is a chat section that you can type your questions there. And so we have already a few questions. Yuming, can you see them?
Yeah.
I will read them loud and you can answer. Anna is asking, could I? Oh, that's not a question. And maybe you can ask. So, okay. So maybe Yuming, you can go through them yourself and read them loud.
Okay. Yes. The first is Michael's question. That is, can you tell us? What do you mean by microcradling? Yeah. Go ahead. Yes, this is just a package in R to quickly process the ordinary or universal kriging, because if we use the common the normally used kriging package, this is very slow. Because we want to interpolate the data into the whole China, so the micro kriging have a special function in the R package. It can give you very quick prediction, but the core function is the same as ordinary kriging. They just use a special function to make your progress quicker, faster.
Yep. And Grant Williamson is asking, can you tell us which variables were most
which
important?
variables are most important? Okay, the most important variable is day of the year. The second one is AOD, but day of the year has a very similar uh, score as AOD. Okay, I will give the most important predictors one by one. The first one is day of the year. Second is AOD. Third is temperature. Fourth is NDVI. Fifth is relative humidity. And sixth is wind speed, and then air pressure, and then elevation, and then the percentage of urban cover, and water cover, and the nearest highway, and then the count of fire smoke spots.
Fantastic. Yeah, and Jeff Morgan from Sydney Uni is asking, what is the source of higher pollution in Western China? Is it dust?
Yeah, that is dust. Yes, that is dust because that is a desert in West China, in Xinjiang province.
Yep,
And
and
most areas are desert. Yes.
Mhm. Jeremy Silver is asking, do you have particular recommendations for application of such methods to relatively data-sparse countries such as Australia? Our land types are not very well sampled apart from urban areas. So it's a different scenario here in Australia compared to China, that you have more densely measurement sites.
Yeah, given because from our data set and the results, we can say the day of the year AOD are the most important variables to interpret the model. So we can say even for Australia, they are very sparse monitor stations. We still can link the AOD and using the day of the year to interpret, and we still need to account for the spatial variation. For example, we can make different cities as a variable in the model to account the spatial variation. And then I think it should be good to link the Australia data and to predict PM2.5 in Australia context.
Yep, and I have a question myself. You touched on the issue of missing values,
Okay.
and
Yeah.
you mentioned that you use the method for imputation as well. Can you
Yeah.
elaborate more on that? The method, were there some of the classical imputation method like KNN, or it was a different method that you used?
For satellite data.
Yes, in generally speaking, how did you deal with your missing data?
For this study, we did not interpolate the missing AOD data, but in the future, we are planning to do, and we have some potential candidate models. For example, we can use the inverse weighted distance model. We have tried this model in the China context, and it performs very good. And also, we want to try the uh, chemical transport model to interpolate the missing AOD data. Um, we will do in the future and to compare which model can perform better
Mm-hmm.
to interpolate the AOD, missing AOD.
Mm-hmm. Thank you. Micheline is asking, was there any satellite data diary?
Yes, we have, but there is no one open online. But you can download the NASA data freely by yourself, and you need to remember after the download, you need to do some uh, geocode validation, and to because it should be adjusted into different systems.
Ivan Hannigan is asking a question about the variable selections in your model, that how it was done and where all the models where they all offered all the variables, and then the gamma had variable selection.
First, we use yes, we have. Yes, we have. We use we put all the variables into random forest model first, and get the variable importance score from random forest model, and we only select the very important variables, and then we put these variables into random forest into these three models, and using finally they use the same variables.
So you were not using any kind of penalized method to choose your variables like that, lasso things like that.
No, we don't. We only use the random forest model to select the important variables.
Anna asks, you mentioned you would like to replicate your data in Australia. Would you be looking at all Australia or particular regions?
Maybe we can start from Victoria first, and then go to maybe go to New South Wales and Queensland one by one. We want to try Victoria first, and then for the whole Australia.
Is there any reason that you decided to pick Victoria? Is it because you're based in Victoria, or there is other reasons for that?
Yeah, the first is we are based at Victoria, and another thing is we have some study in Victoria. For example, we have a Hazelwood study. We want to try to compare if our PM2.5 predictions are better than others or worse than others. If we have a better prediction for PM2.5, we can link for our PM2.5 data with our Hazelwood study.
Yep. Paul asks whether you checked for collinearity in your variables or autocorrelation to remove confounding variables.
Yes, we have tried, but we can't remove all of them. And one thing is, for the prediction, from the biostatic perspective, if we want to only look at the prediction, we don't need to worry about the collinearity. But if we want to look at the specific association between temperature and the PM2.5 or relative humidity of and PM2.5, we need to worry about collinearity. But if we only look at the prediction, not the specific association, I don't think we need to consider collinearity, because even there are collinearity, but the prediction is high.
It leads me to another question of mine, that did you do any pre-processing, like applying PCA, centering, things like that as well on your data, or no?
No.
Okay.
Because we only look at the prediction, not a specific association.
Sure. Ivan has another question. Can you describe again the mixed model of AOD? Was it used to blend two AOD products? He didn't fully understand. Yeah.
Yes. Mixed model of AOD. Oh yes, that is blend two, but that is a mixed here. We give a relationship between the two sources of AOD. We give a weight for the dB to predict DT, and reversely, we weighted DT to predict dB, and then we combine these two together. This is mixed blending, yes.
Is there any more questions? While we're waiting for more potential questions, Yuming, you mentioned the package you use, Random Forest, and
Yes.
I'm aware of another package that is known to be more efficient. I'm not sure whether you have worked with it. It's called Ranger in
Oh, yes.
in R. Just want to know your thought. I've been told and I've heard that it is more efficient and it's now more advisable to use Ranger over Random Forest. What are your thoughts on that?
I have saw that, but I have not used that. Some of my colleagues are using that. Yeah, we have not compared which one is better.
Okay.
Yeah.
Sure.
But it seems the random forest package is a little bit better than the other one. Someone has told me, but I didn't do that.
How long roughly on a normal computer took you to build the model, to run the model?
For the
Random forest model, yeah.
For random forest model for the China it should be 10 hours.
Okay. Including all the cross validations, probably, right?
Yes.
Okay, so if there are no more questions or comments, Yuming, do you have any final comment that you want to add?
Yes. Thank you very much for your attending this seminar. And if you have any questions, can email me or call me, and I'm happy to collaborate for your study. Thank you.
Fantastic. Thanks again, Yuming, for an interesting presentation, and thanks to all who attended. And I would like to mention that today's seminar has been recorded and it will be available on CAR's website. And I think it's now time to end today's webinar. Have a good day, everyone.
Yeah. Thank you all.